Section 20.4, electric power. So we're going to consider a setup where we have a battery that is then powering some electrical device. So this could be our classic MP3 player or a classic phone like this. I just love seeing this relic of a flip phone. What a throwback. We're going to consider the amount of charge delta Q that's flowing through a battery where the potential difference between the battery terminals is given by V. All right. Now, if we want to connect this to power, it'll help us to first remember what is power. So how do we define power, at least from 2A, as a basic idea? Well, remember, power is energy over time, specifically a change in energy over a change in time. We can write our change in energy all over our change in time. Now, as we're thinking about this scenario, we want to write this power in terms of this charge that's flowing through the battery and the potential difference between the battery terminals. And if we know a charge and a potential difference or voltage, we can use that to describe the energy, right? Remember, we can say that the energy, specifically the change in electric potential energy, which we could then say is the energy, is equal to delta Q times the voltage. So that's what we're going to use here. If we plug in, our power is equal to the energy, delta Q times V, divided by the time, delta T, and then we're going to group it slightly differently to help ourselves out. We'll put the deltas over each other. So delta Q divided by delta T, and we're just going to move the voltage to the outside of this. Because it's multiplication, the order doesn't matter. So we're free to move the voltage to the outside. And then we notice this grouping, we have delta Q over delta T, the change in charge over the change in time. That's our definition of current. So instead of writing it in terms of Q and T, we can just write it as I, or that the power is equal to the current times the voltage. This is a pretty powerful result. So here's it written formally and simply. When there is current in a circuit as a result of voltage, the electric power delivered to the circuit is P is equal to IV. This is another equation that pops up all the time. In addition to Ohm's law, we use this P equals IV quite extensively. And the unit of power is the watt. Exactly, it's the watt, right? Unit of power is watt, which is a capital W abbreviation. Now, an important note here is that though we can calculate power with current and voltage, many electrical devices are essentially resistors, like light bulbs. We can treat those as basically just resistors. So if we want to calculate the power that a light bulb is using, oftentimes we'll just work with more the current and the resistance. We don't even need to know the voltage. So to do that, we can start with our P equals IV and then use Ohm's law to help ourselves out. So we'll have the current, and then instead of the voltage, we'll plug in that V is equal to IR, and then we no longer have voltage. We just have I squared times the resistance. Similarly, we could eliminate the current by plugging in for the I with V divided by R. V divided by R times the voltage will just give us V squared over R. So that's another way we can calculate the power, by using our P equals IV along with Ohm's law to help us out. Let's check out an example of this. So the power and energy used in a flashlight. We're back to our good old flashlight here. They're a reliable thing to have. So in the flashlight, the current is 0.4 amps and the voltage is 3.0 volts. We've seen those numbers before. Find A, the power delivered to the bulb, and B, the energy dissipated in the bulb in 5.5 minutes of operation. Okay. So since we have the current and the voltage, here we aren't asking for the resistance, we're asking for the power. And we remember power is equal to current times voltage. So we're in great shape. We don't even need to do much manipulation there to solve it. What about for finding the energy dissipated in the bulb? Well, if we want to solve for energy, we can remember energy is closely related to power. How? Remember, power is energy divided by time. So that tells us energy will be power times time. So we can get our power from A and multiply it by the time. What's the time here? The time is 5.5 minutes. Now, are minutes our SI unit of time? Not quite. So when we plug in for that time, we're going to need to make sure to convert those minutes into seconds. So 5.5 minutes times the conversion. Remember, we want to cancel the minutes and end up with seconds. So I'm going to put seconds in the numerator and minutes in the denominator. And then we can look and say, okay, I know there's 60 on one of these and 1 on the other. That's right, there's 60 seconds in 1 minute. And that should allow us to calculate it. So let's take a look. So P equals IV. We have our 0.4 amps times 3.0 volts, comes out to 1.2 watts. For the energy, it's the power times the time. So 1.2 watts from A multiplied by 330 seconds, or 5.5 times 60 will give you that amount of seconds. So that comes out to 4.0 times 10 to the 2 with what units? Joules! Back to our favorite unit of energy, the joule. So this wraps up the section on electric power.